Thank you, Doug. All right. Hi, everyone. I'm Jack. I'm going to be talking about multi-stage Rosetta scripts with JD3. And I did want to mention before I started, so in my title, Rosetta scripts JD3, this is not Jared's Rosetta scripts JD3 with very common vocabulary, so it might get confusing. There was actually a brief time where I was going to name mine JD3 Rosetta scripts, and I think that would have been much worse to have those two. Just to briefly describe the difference, Jared's has got many features. The main selling point, is Jared here? I want to, okay. If you're shaking your head, I want to stop. So is it fair to say the main selling point is that it's, if you have many different scripts that you want to run, or similar, they can be, but this is designed to help load balance them over many different CPUs, where what I'm about to present is when you have maybe many input structures, but just primarily one protocol that's very long, a way of shortening it. And so just to set this stage, that's we might work on making them more compatible together, but that's the difference to have in mind. So Rosetta scripts, movers and filters, this is my Rosetta script. And the way that they traditionally get run is you just have many different trajectories, maybe only one if you have an instruct of one, but normally you'd have many trajectories. Rosetta runs the first one, runs the second, third. If you have more CPUs, it can do them in parallel, but it does them in whole chunks. And multi-stage separates them up into user-defined segments, runs all of the first stage, does some analysis, which I'll talk about, all of the second, then all of the third. So all of the trajectories kind of step through the process together. And this allows you to do a few things. The first being filtration based on your global rank of the trajectories. So Rosetta scripts has filters, but their cutoffs are predetermined, and it's hard to estimate sometimes what value you will need to provide to your filter so that you get a certain percentage filtered out or kept. And when you do all of the first stage together, then you're in this void in between. You can know which trajectories are your 25 best or 50% best or whatever you want to choose. So you can drop your bottom whatever percent user defined, and you can do that for each stage. So you end up doing less work, which you can do with just normal predetermined filters, but it's more difficult, and those cutoffs tend to be conservative because of that. And another feature is once you do this cutoff, you can just fork the survivors so that, for every trajectory that survives this first round of cutoffs, you can have it spawn into two or some number of new trajectories, and those will continue, and they'll just have lives of their own. And in practice, I don't use that very often because I don't want to end up with just a ton of clones or near clones at the very end of the protocol. It's easy to imagine that these two will be very similar. And if they're similar in a way that's better than this, you might sacrifice, you might filter out this first one in favor of having clones. So recently I added to master two different ways to maintain diversity. The first being that when you create forks, you can add some kind of limit. It doesn't have to be one. So of all these new trajectories I create, just say how many you're going to keep, and it picks the lowest n energy trajectories and discards the rest. The second way being that you can cluster based on everything, based on some user-defined. It's not traditional clustering that we usually think of. You have to create some snapshot of the pose. You're not going to have them all in memory at once. But based on like sequence or some jump or some metric that defines distance between poses, And then that way you can whittle down and keep a diverse set of trajectories. And between each stage, you give one or multiple input poses, and by default, all of the results are pooled into the same, they're merged into the same pool of results. You can also elect to define when that happens. So maybe after your first few movers, you're not quite ready to combine them into one pool. You'll just keep like 1/3 the size of, it'll be evenly dispersed, and then you can just choose when they all get put into the same pool, and will no longer be distinguishable. To test this out in a toy example, I played with Bachelor Axe. Multistage Rosetta scripts abbreviates to MRS, so I just have fun calling every protocol misses that protocol, and that's the naming. Faster lax alternates between fixed backbone sidechain packing and minimization, and I decided to call one of these repeats the stage, and after each stage, do some filtration. Bachelor Axe has been done before in Rosetta. It's so I thought it'd be a good toy example just as a sanity check and to just show that this works. And so I ran the, sorry, let me go back a sec. I ran the ab initio demo in the demos repository, and but without that final packing step, so it's just centroid mode, and generated 30,000, they're relatively small, but 30,000 structures. I'm showing how many structures go through each repeat of FasterLax. So for Rosetta scripts, all 30,000 structures go through 4 repeats of FasterLax, but for multistage, we do all the structures go through the first repeat, then we remove the bottom 75%, and the remaining 25% go on to the next repeat. Then after that, the remaining 25% go through the next 2 repeats. So there's 3 stages here, 1 stage, 2 stage, and 3 stages. And so this is faster, ran in just over 1/3 of Rosetta scripts time. And just to show that the results are similar at least, I ranked all of the results from the output of each one, Rosetta scripts in orange, multistage in blue. By chance, multistage's best structure is a little bit better than Rosetta's best structure, but in general, the lines are pretty close, up to about 100 structures maybe. So the idea being that you don't lose that much in this time that you're gaining. A better scientist would have run this a few times and had error bars and stuff. But, so now in terms of how do I run this, I tried to keep the interfaces similar to normal Rosetta scripts as possible, but it is built on JD3, so there is some new XML tags that will be in play. So as Jared mentioned yesterday, JD3 uses this job definition file, which has job tag and then common. Normally, they'll actually be in the reverse order, common then job. I selfishly, for multistage, just switch them. And the stuff in job is like input-output information. So in this case, this is going to replace the -S or -L flags. This is how you give the pose. And then in common goes most of what we picture as being current Rosetta scripts. Your Rosetta script would go in common. To dive into a little deeper, I'm calling data map info things like residue selectors, task, everything in Rosetta scripts except protocols, things that you define that you can call from movers. The movers are a part of this as well. Then job will have things like input and output. And then common, after all the movers, and so you have protocols. And that's the part that has probably changed the most from normal Rosetta scripts. So there's a little bit of foreshadowing white space here. But this is, the add is still there. You can still call add. There's going to be a few more things. So for this Bachelor Axe, I have these 3 movers, relax with 1 repeat with 2, relax with 1 repeat for stage 1. Stage 2 is relax with another repeat, and then relax with 2 repeats for the final stage. And I gave 30,000 input poses. I ran the stage 1 is just stage 1 mover. I sorted by just ref 2015. That gave me, and I filtered down to 7,500 poses. Stage 2, sort down to 1875 poses. Stage 3, sort, and there's no reason to filter between your final stage and outputting PDB. So we're still at 1875. So the way to reflect that into the XML is to add these sort tags after each stage, and you just give it some filter, and it will take the floating point number returned by that filter and use it as a sorting metric. There is an option to say positive is better, but by default negative is better. So in this case, I have this filter that takes beta November 16 scores and ranks them. And then you surround each stage with this stage tag. All of the options for the stage tag are very verbose, for now at least. And number of runs per input struct, it's basically end struct. So for all 30,000 poses, we want to run stage 1 once, and we want to keep 7,500. Then for all 7,500, we want to run stage 2 once, keep 1875, run all of those once, keep 1875. So there's protocols is a little bit messier. Now there is an there's a converter. If you have a Rosetta scripts and you want to turn it into a multi-stage Rosetta scripts, you just feed in the Rosetta scripts and it will convert for you. It's not completely intelligent. You still have to do some things. It won't fill in these numbers, for example. It doesn't know how many you want to keep, but it will create the XML skeleton for you, and you can just fill in. It'll even create to-dos to tell you what you still need to do. There is I created a wiki page. You might recognize that little GIF, which describes as much as I can describe. There are a few things that I'd want to point out. So I guess first the jargon page is really useful because I tend to get caught in my own vocabulary a lot. So and it's more developer-based jargon than user-facing. So there might be something that I wrote that I think makes a ton of sense that you might not. So if something's not clear, you can go there. The XML format basically shows a little bit more in depth of what my past few slides showed. It also mentions how to run the script converter. You can also do reverse conversion if you have a multi-stage script and you want to convert it back, which is useful for debugging if your multi-stage thing crashed and you wanted to just run it quickly locally. And saved options I have time for. I might go into a few of these. Before I do that, compiling and running multi-stage. So this has all the command line options that you might want to be interested in. I don't know if you. There's a page on how to cluster between stages. One feature, the next feature probably that's going to be added is checkpointing. So one of the big drawbacks that I kind of brushed past is that by doing all of stage 1, then all of stage 2, then all of stage 3, if you crash in stage 2, you don't get anything. Or stage 3, you don't get anything until the very, very, very end. At UNC, we have our supercomputer organizes its queues based on how long something's allowed to run. And so if I submit to a week queue and my job takes 8 days, I don't get anything. It will just die. Where with Rosetta scripts, you just pick up where you left off. So the next thing that we'd like to implement is checkpointing so that you don't have to start over. And I also have examples. So each of these pages down here have a script that, so the Bachelor Axe page, oh, that's very small text, I'm sorry. Say something next time. The Bachelor Axe page has the script I used to generate the data I showed you. There's also data map overloading is a term I came up with. So you can also have residue selectors and stuff in the job tag. so that each structure you pass in, you might need a different res file or something. And as long as you give it the same name, then whatever res file you give for that job will be the one used for, I don't mean file name, I mean a residue selector name. I'm having a hard time describing it, so I'll just go to the page. So this job, read res file 1, and the name of the residue selector is RRF. This next job has a different file name, but same read res file name. So later in common, when we want to call RRF, it will just go to whatever residue selector is relevant for that job. And you can define defaults in common. So I think, I don't know, somewhere here, you can have like a score function in common, and if that score function of that name is not defined in job, it will be the one in common that you use. So you might have 10 jobs, 9 of them use the common score function, and one of them uses a different score function by the same name in its own job tag. I'm at yellow. Okay. I guess the only other thing I wanted to mention, so the stage tag itself has, this is where most of the features that I mentioned in the first few slides would be. So there's a paragraph or two about each one, and one that I didn't mention is result cutoff. So a useful feature I found, especially lately with docking, is if I know how something's going to dock or how I want it to dock, I can apply like hard filters so that if you don't dock in the right region, it will die. And then I can run multi-stage, well, a stage with a very large number of runs, but I can tell it to stop early once it gets a certain number of results. So dock 1,000,000 times, but stop once you get 1,000 results. And that's been handy. I mentioned that these names are so verbose. This one's so verbose, it actually goes on to the next line. You can also have movers that return several results. HMNet, for example, they return multiple poses, and you can just, if I go back here, each pose will have its own like different fork that the mover returns. So you wouldn't be using the multiple pose mover anymore. You would just allow movers to return many results. All right, so with that, well, I'll just skip here. I'd like to thank the Coleman Lab and especially Andrew, who's been helping a lot with the JD3 interface, and then everybody who've had to help me on GitHub. I needed a good amount of help, especially Sergey if he's still listening. And I have a link to the wiki I just showed you. And if this new interface doesn't give you all of the functionality of JD3, so if there is still functionality that you want, I wrote a walkthrough for writing your own JD3 job queen. It's like a 10-step, just writing something simple. So that might be worth a look. All right, and thank you.
Okay, that looks really, really useful. Particularly, it captures one of the most common workflows that we have, which is do a lot of sampling, then do some filtering to collect a small number of results from the large number of sampling, and that small number of results becomes the input to the next stage where you do a lot of sampling, and then one little thing that I'd request or suggest, actually 2 little things that I would request or suggest. One would be, in addition to being able to specify the number of structures to keep, being able to specify the fraction or the percentage to keep would be useful.
Yeah, you're right. So like optionally one, pick number or pick fraction.
Well, yeah, one
Sure.
or the other.
That's more of sorry to interrupt. That's more of a.
That's a detail.
Once it gets parsed under the hood, that's not too different. So that will be not too hard to implement.
Yeah, that's a detail. The other would be associating that with the sort rather than with the stage.
Yeah.
So that you can have multiple sorts in the same stage. So I could say, for example, in stage 1, I want to I want to keep the top 10% by energy, and then from that top 10%, I want to sort again by DDG or something, and take the top 10% by DDG.
No, I agree. Right now, sorry, I'm trying to find the slide. I guess I just won't. You only get one sort. You have a bunch of ads, and then it has to be followed by a sort. There's been demand or interest in having ads after the sort, like a finally block. But you're saying maybe multiple sorts where the only way to do that now is to have a next stage after that is just a sort. So it can be done, but it's kind of ugly. But that's something to consider. Thank you.
Quick, Stephen?
No. I'll hold it.
All right, in the interest of time, let's give Jack a round of applause.